So, good morning. And today, last couple of lectures we spent in trying to, very conservatively figure out how two inertial observers will, how the electric and magnetic fields mix under how the electric fields and magnetic fields mix between these two observers. And we worked out this formula to order U by C. Okay, and the key point here, a couple of points here. First one is that we did not need to make any assumptions about, that U had to be comparable to speed of light. These require U could be any as small as you wish compared to C. And so this is just a simple this thing formula, and this is we are working in Gaussian units where E and B are measured with the same units. Okay, so U by C, you notice here, is dimensionless. U has dimensions of speed, so does C. Okay, so we get nice symmetry, and there is a slight asymmetry between plus and minus, but that is to be expected. Okay, so, and this is in Gaussian units. Okay, are there any questions and comments so far about this statement? Okay, I guess not. So my next point is that it turns out that E and B, they are more complicated objects in some ways, and so it's easier to work with the scalar and vector potential. And so we have this. So observer A will write this formula. If phi and A are the scalar and vector potentials in which observer A sees, then E is minus gradient of phi minus 1 by C dA by dt. Okay, so you might, in electrostatics, dA, we assume that the second term won't be there, but in electrodynamics, which is the most general thing, of course this term is there. Okay, so this is the most general connection between the electric field and the scalar and vector potential, and B remains del cross A. So this is the definitions. If you're given E and B, so what we want to do is to plug, so observer B will do something similar, except everything which we see here, he or she will add primes to it. Okay, so are these formulae clear to you guys?
Yes, sir.
Okay, so this is also our idea is we know how E prime and B prime are related to E and B, and so now the operating question is how phi and so I should put primes here also. How phi prime A prime. So we want to work out how phi and A and phi prime and A prime are related. Okay. So, but we can again use similar methods that we had and leave only one coefficient. So we want to write something like this: A prime. We want to write A prime as a function of U. Of course, C is there as a constant. A and phi, and that's it. Similarly, we want to write phi prime as a function of U, A, and phi. Okay, so this is just a guess. And again, we can use some facts. Phi is a scalar, and what kind of vector is A? Is it polar or axial? That's all I'm asking.
It is.
So B is, so you can go back here. It's not so hard. B is axial vector. So, but it's del cross of A. So for this to work, A should be a polar vector. Okay. Just looking at this formula, you can figure this out. Okay. So we can only write polar vectors. Okay. So we will write some B1 U by C times phi. Again, we are only interested to this order. Similarly, The zeroth order piece is very clear. When you put u equal to 0, phi prime beta b equal to 5. Okay. So now we want to construct a scalar which will involve u. Okay, so the only way we can do it is to dot it with something, and there's only one vector, and that's a. And I'm putting by the c to make things b1 and b2 dimensionless. Okay, is this clear? So there's nothing. I mean, I'm not doing some deep thing, but I'm anticipating, just like we did before, that this is the way the formula should be, and we are only interested to order u.
So the only reason we are able to eliminate the presence of divergence in this is to maintain the fact that A will be polar. Is that correct? Like in our assumption of A dash, we are not considering the fact that there may be a divergence or a curl of something.
Good point. So let me just think about that. So so the thing is, so point here is now what kind of term? So the kind of term. Let's try to write some term, right? I mean, so let us see. So we have to use. You are saying I should use u. I can use divergence also, and a and phi, right? So let us ask, how do we construct? And it has to be linear in u. Okay, so maybe we could write something like u cross gradient phi, right? We could have written something like this.
Yes, sir.
Okay, and a little thought will tell you that this is axial.
Yeah, but we need on the LHS.
So we need. So here we could have added this term, but it will mess up the fact that A is polar. So it's an axial term. So there is a term which we maybe could have come. Okay, what I'm saying is, because it's axial, it's ruled out, not allowed. Similar thing we could have done. We want to ask, we want to add some other, so we could have written something like, del dot A for phi. No, I don't even know how to write. Yeah, I can't even write a term. I don't know. You just try to see, you'll find you cannot write a term. Okay. But there are other arguments also, but at this point I don't want to get into that. But you can see that this term I cannot add. You agree with that?
Yes.
Okay. Good question. So we need to figure out B1 and B2. Okay. So but we will also need to have the relation, to use the relation, because del is coming, which involves x coordinates. Use the change of coordinates. Okay, both space and time for the two planes. Okay, so okay, very good. So what we will do is we will write x prime equal to x minus u, okay, u t plus. Now this is what I was explaining last lecture, that I can add. I'm saying there could be corrections of the order of u square by c square, and we can also make it like this. So ct as dimensions of length. So we can also write ct prime will be equal to ct. So by the way, I'm assuming that observers A and B align their axes, because I don't want to worry about rotations. I'm also saying maybe at something the time they match times and things like that. So there could have been additive constants which are boring, and I just don't worry about them. Okay, plus A3. Now there is a term I could write here which I couldn't have written otherwise. So, so then, so the remark which I made last time also, the Galilean boost implies A3 equal to 0, right? And no higher order corrections. So u square by c square, all those terms, all this thing. Okay, is this clear? So, but I'm trying to be more general here, and so if Maxwell's equations were compatible with Galilean boost, then A3 should be 0. Okay, we want to check that whether it will happen. Is that clear what we are doing?
Yes, sir.
Okay. Okay. So we have three constants to fix, and I'll fix it by going back to, so go to this equation here and substitute for E in terms of phi prime A prime, and then substitute phi prime A prime with the way we did, and do the dels and del prime, two partial derivatives, etc. This formula is a little messy, and it's but straightforward. Okay. So we will need some formulae. So we need formulae from multivariable calculus.
Sir, it's B3, not A3. It's B3. You've been using B.
No, so okay, so B1, B2, you want me to call this B3? No problem. I called it A3 last time. That's why I put A3. Last lecture I defined this thing. I had two constants there. I called them A1, A2, and I called this. So yeah, I can call. So what do you want? I mean, you want me to call it B3 Siddharth? I can do it.
Okay, I thought it was a continuation of the constants from a previous page.
Yeah, no, actually, yeah. I mean, I wanted to be consistent with last lecture. That's why. That's why I put A. Not that I am very consistent, but okay. So we need formula like this. You know, d by d xi prime will be equal to, you know, sum over j dxj by dxi prime d by dxj plus dt by dxi prime d by dt and stuff like this. D by dt times sum over j dxj by dt d by dxj plus dt by dt prime right. You know this formula, right? Okay, and okay, just 1 second. Okay, okay, so I'm just setting things up, and so I also want to simplify things, so I will just define something. So let x0, let's put uppercase hereafter, just for a moment. Everything x0 be ct and x0 prime be ct prime. Okay, so everything has dimensions. So we can write that formula as a nice matrix formula, which is x0 prime, x1 prime, x2. So this is just the same formula that we have here. I call this x0 prime. Okay, I'm just writing it out in this matrix form plus order q squared by c squared. Okay, is this clear? This is just rewriting the formula. Okay, and so we will. What we need is really inverse of this matrix, etc. I'll leave it as an exercise. Okay, so exercise. Show that there might be order u square terms. We won't worry about them. Okay, is this fine? So this is just an exercise. So I've just done some calculations. So now we can compute. Now I'll just sketch of the computation. I won't show the computation. Okay, so please fill in the details yourself. Okay, so that is the thing. So let's just I'll label this equation. Yeah, let's call this equation 1. We'll call this equation 2. This is truly equation. This is also 2. Same equation. So I'm just writing the same thing. And this we'll call equation 3. Okay. So first step is you compute, or rather express E prime and B prime in terms of del A and phi, and of course U. This is what we want to do. So E prime, so for instance, B prime is del example. Okay, so del prime we have to replace with this equation 3, and A prime we'll use equation 1. First of equation 1, right? We plug this in, etc. Okay, and rearrange. Okay, so we are doing this. I'll draw it as a this thing, E prime and B prime. You start with these, make the things, and now you go into some expression which has U, del, A, and phi. Is this clear? What we are doing? I'm jumping steps, but now, okay. So this is just that thing. Now, re-express in terms of E and B. That's what you should do. Is this picture clear? What we are doing? So there are some identities, etc., that you will need. Okay. So, and now this. So now we can compare these two, right? Now we know how E prime and B prime are related to U, E, and B to order E square. But now if we go this route, or we go this route, let's remove this. Okay, both routes should give the same answer, right? You go either like this or go like this, you should get the same answer. Is this clear? Okay. So So root 1, this we'll call this. This is root 2. Okay, both roots will agree. Okay. So exercise. Okay, this implies that we need A3 to be minus 1, A1, sorry, B1 should be minus 1, and there's one more. That's also. Okay, this implies or needs. Okay, so you need all these guys to be minus. Is it clear? I'll rewrite it again. Okay, it's straightforward algebra, but there might be one or two identities that you will need. Okay, so your hint is you'll need this identity, I guess. U cross del cross A is equal to U dot del of A minus gradient of U dot A or something like this you'll need. Okay. This identity might be needed. And such vector identities from vector calculus. Okay. But what is important here is, first thing is that there are more, if you look at root 1 and root 2 agreeing, there are many terms. So it's not like there are just 3 terms. Okay, if there are 3 terms and you fix 3 numbers, you're done, right? But there are more than 3 numbers, 3 terms. So actually, it's the fact that there exists something is important. First observation is that there exists values of B1, B2, B in A3 such that these in mathematics they'll say this diagram, it commutes. It doesn't matter which way you do it. Okay, so this is the first statement, and most important statement is A3 is not 0, implies Galilean boosts don't work. Is this clear? This is very, very important. Okay. Do you understand what we have done so far? Any comments or anything? Just let me know, because I have not done the calculation. It usually takes way too much time, and I don't want to waste time. Okay. But I strongly recommend that each one of you do this calculation. Okay. So now we have got all these values. We can go back and plug them into equations. So now we can. Okay. And now I'm going to do it. Okay. So I'll do that, and that's so let's do that. And okay, so what we get is quite nice, very interesting. Okay, second term is just, I put a C here because x0 is Ct, remember that. But what is very interesting is when we write down what phi should be. Okay, so here in these two places I put b1, b2 equal to minus 1, and here I put, which is the one, this is the one, I put b3 equal to uh, minus 1. Okay, but do you see some interesting symmetry here between these things? Let us now look at these two equations, this and this. Do you observe some nice symmetry between these, I mean similarity rather? Does anybody see a similarity?
Yes, the first one is like a scalar and the second is a vector.
Yeah, but
and
no, but yeah, that's right. So what we have is, so x0 prime, and so what you look at this here, you have x0 and x here. You just replace x0 by phi, you replace x by a to get this. Come to the next equation, same thing, replace x vector by a prime. So this will become a, and x0 should be replaced by phi. So you see that these are actually identical, similar equations. It will become even more dramatic when we write it as a matrix equation. Okay, so we will write this. Both equations in a manner that highlights the similarity. We didn't know this, right? Before we started, we didn't know this. This is kind of unexpected. So let me define a 4 vector. Okay, a 4 vector V consists of scalar under rotations and some other vector under. Okay, so let me write what I mean by this. So this is some scalar under rotations, and this fellow is vector under rotations. Okay, so two examples. X4 vector, I'm just putting underline to tell you that, is x0, x1, x2, x3. And similarly, I'll write A 4 vector. What should I write? The first guy should be a scalar under rotation. The next three entries should be, right, A1, A2, and A3. Okay, so now I will write, so we'll rewrite both equations can be unified in this form. So we can write it as V prime equal to okay. Okay, this is something we couldn't have guessed. That this combination, both of them transform linearly and with the same matrix. Okay, and so we will call this, we'll give this guy a name. Okay, we'll call this guy. It's a boost, but it's infinitesimal boost. So we'll just call it infinitesimal Lorentz boost. Okay, is this clear? So let me now call this matrix. So let let me define something which I'll call as phi I, which is just this ui by c. Okay, so this is a variant of phi. This phi I used for scalar potential. Okay, hopefully you can see there's a distinction between these two guys. Okay, and let lambda be this 4x4 matrix, which I'll write here as 0, minus phi 1, minus phi 2, minus phi 3. Okay, and of course, yeah, that's all. I just want to write it this way. We'll call this phi, we'll give it a name, we'll call it, it's dimensionless. We'll give it a name, we'll call it rapidity. Okay. And now once I have this, you can see that V prime equal to identity plus lambda plus there are corrections. Okay, so this is I have simplified it to write it in a short form. Is this okay? So it's the same formula which we had here. These formulae, at the end of the day, with all these definitions, etc., it takes this nice form. Okay. So, so in some sense, lambda, this knows about infinitesimal. So if lambda is 0, it becomes identity. So V prime will be I. Okay. So maybe these terms you can think of them as order lambda square if you wish. Okay. So now we will make an assumption. Finite Lorentz proofs are given by exponentiation. Okay, so that means we are saying that that there is a Lie group. Okay, this is an assumption. Okay, we can prove it, but I'm just so I can put this assumption. So equivalently, we can write this claim. Okay, and this is finite. Okay, is this clear? So this is now a very strong claim. Okay, but you can actually prove it. You can go back and like I said, we can in principle work out the order u square by c square terms, etc., etc., etc. Okay. And only one thing I need to explain is that I didn't call phi I as velocity. We will see that what will happen eventually is that phi I won't be the velocity. It will be something else. That's why we're going to do that. But for small rapidity or small velocities, what we will see is that this is the kind of the equation. Okay? So we could say something like, actually it turns out that it's like order u square or something like that exists. Okay. But now I'm just saying here from our viewpoint, we just know infinitesimal, which means u is very, very small compared to c. So we don't worry about that. So this is a little bit of a cheat or kind of hindsight. So I'm just calling it 5 instead of calling it u by c. Okay. Is this clear? Because we will see an independent way of getting what u should be. Okay. So exercise. Just do a simple case. Compute exponential of this matrix 0, minus 5, minus 5. I'll let you do this computation. Okay. And let me also call this matrix, we'll just call it capital lambda. Okay. So just some notation. Lambda is finite Lorentz boost, and little lambda is the first order piece. Okay. So maybe I'll write this out. Okay. So you can show that this is equal to okay. So this is so what we see here is this looks similar to the rotation matrix in 2 dimensions, except sine and cosine functions are replaced with hyperbolic functions. Okay. So I'll use this computation. So for example, suppose phi 1 is non-zero, then lambda will be made up of 2 by 2 blocks, which is exactly like what I wrote here. So phi 1 okay. So this is so you look at this 2 by 2 block. What is it acting on? It only acts on the 0 and 1 space, and 2 and 3 nothing happens. This is what this is. Okay. So is this clear?
Yes, sir.
Okay. So let us so for instance this will imply that Ct prime equal to cosine phi prime by 1 Ct minus Okay. So what we will call this? So this is we'll give this a name. We'll call this a Lorentz. This is a Lorentz boost in the x direction. Okay. So in particular, if we try to look at x1 prime, this I can write it in a particular way. Cosine phi into okay. So if you look carefully, you can even argue what this is. What this will say. This says that the velocity, the inertial frames, okay, move with relative velocity proportional to tan hyperbolic of phi, of course, along the x direction. Okay, so now you see that what we see here is, so what this means is u1 by c is equal to tan hyperbolic of phi 1, which for, if you know, for small y1 is this plus order y1 cubed. It's not phi 1 square because tan hyperbolic is an odd function. Okay, so you see my claim. We will make this more precise maybe in a short while, but what I'm saying you is that this combination should have been x minus ut, right? So you see how what is happening is that u by c becomes tan hyperbolic of phi. Okay, so this is what I was saying. This is not something which is obvious, at least to me, and so that is why I wrote this and said, like, we re-express everything in terms of rapidity. So rapidity and velocities have a more complicated relationship. This is what it is. Perfect. However, for small values, they agree. Okay, of course, up to factors of phi, of c. Is this point clear? Okay. So let's make this more, little bit more paka. Okay. And ask. So I'll just pause here before proceeding. And okay, so are there any questions and comments? Okay, so we will look at, so what are we look at some nice properties. Okay, so the first one, which we already saw, is yeah, so now what I want to do, what is the property I wanted to, yeah. So consider, so we'll do this. X direction. Okay, x1 direction. Okay. Then we can see that the 0 square prime V1 prime square is actually equal to V0 square minus okay, and it follows. This needs only this simple identity that cos hyperbolic phi square minus sine hyperbolic phi square equal to, what is this equal to? 1. Okay. Just like under rotations, okay. So this is similar to rotations. Preserving the length of a vector. Except there's a funny minus sign, right? This is the same minus sign which appears here. Okay, so what you should do is go back and plug all these things. You should see this. Okay, so this is what is happening. But more generally, but what is happening? There's still something, because it's a boost in the x direction. Then we also know that V2 square prime equal to V2 and V3 prime equal to V3. Okay, so more generally, an arbitrary boost in any direction okay, something we'll write like this, norm of some 4 vector V, okay, norm square we call it, okay, and this norm has a name. It's called the Minkowski norm. Okay, this is weird in the sense that so it does not imply V equal to 0. In Euclidean norm, which is the standard norm, if I made this plus, okay, then that we'll call that Euclidean norm. But this, we don't have that freedom. We get this funny norm. We have to live with this, right? You can see, right? If this is equal to 0, all you need is V0 square to be equal to the norm of this 3 vector. That's all you need, and that's possible. Is that clear? So this so Minkowski norm is weird. It's not like our norm of this thing, but this is a natural norm of a 4 vector. Okay, so this is the thing. The Minkowski norm okay is preserved under rotations. Can someone tell me how? How do we see that? So this is the norm. So let me box it. Can someone tell me how?
It's a scalar, right?
Yeah. So V0, so let's look at it. Under rotations, where V dot V, looking at this is a scalar. And V0, so we said we created a 4 vector by taking a scalar and combining it with a 3 vector. But in the norm, we are only seeing scalars under rotations coming. Okay. Is this clear? Okay. So that's what happens. The Minkowski norm is preserved under rotations. Okay. Of course, in addition to Lorentz boost. Okay. So in problem set 12, we will see something interesting. We will see that the composition of two boosts okay, is not another boost. Okay, rather it is a boost plus rotation. So it's much more complicated. You remember, if we did a Galilean boost along x direction with some magnitude u, and if we did a Galilean boost along y direction, we would get another Galilean boost, and the velocities will add according to the laws of vector addition. This is not true. Okay, and we have to live with this. Is this point clear? So this is a calculation. We have to live with whatever we get. Okay, so now we will do a definition.
Hello, sir.
Yeah, go ahead.
Can you please repeat again that how you said Minkowski norm is scalar?
Under rotations.
Yeah, scalar under
Rotation, I'm saying
rotation.
rotations preserve. I said here the Minkowski norm is preserved. So under rotations, V will go to V prime and V0 will go to itself. But V prime dot V prime, V vector.
V prime to V
So what
prime
I'm
dot
saying
V
is
prime
V
is
prime
not a
will be.
scalar under rotation.
Why? Oh, this is news to me.
I mean, okay, under rotation it is.
Under
Under
rotations. Under rotations.
yeah.
I'm putting 3 vectors. Notice here. Okay.
Yes, sir.
Okay. That's what I'm saying. No. Under boost, we needed these two. See, this and this will mix. So boost is more complicated. Okay. So definition is define. Definition is let yeah, not let. We'll just say the Lorentz group is a set of linear transformations that preserve the Minkowski. Okay. So next lecture, which is tomorrow, we'll work out what are all the possibilities. So we already seen two things, two ingredients. One is Lorentz boost and rotations. They all form part of the Lorentz group. Are there more? Okay. So we'll see there is parity. So there'll be discrete groups, but there'll also be something new, which is time reversal. Okay. So we'll get this definition. I don't want. Okay. I'm calling this a Lorentz group. Okay. Okay. Good. So I'll pause here for questions, comments, anything.
Sir, while defining the 4 vectors, you just said that we just take a column whose first entry is a scalar and the other 3 is a 3.
Yeah.
So, like they can be any, or do we put the transformation property?
Yeah. So it should come with the so Lorentz. So we'll define a 4. I have to define now a 4 vector as to how it transforms under Lorentz boost, Lorentz rotations, blah blah. Sorry, Lorentz boost and rotations. Okay. So that now it's like I didn't do it like proper definition. Now we will define a 4 vector under the Lorentz group, etc. It'll come back to those things which we already saw. I haven't proved it yet. It'll come. We only saw it happen for A and displacements, right? It's space-time. Okay. So we'll see that many other things which we know in mechanics, they will combine into 4 vectors. Sometimes there are a class of things where it will be very, very nice. In other class, it won't be. So we will see examples. We will see all those things next lecture. Okay. So right now it is just, we have only 2 examples to go by. But the whole point here is that we believe that these are all properties of 2 mutually inertial frames. They will be relating those guys, and so it shouldn't depend on what field you are looking at, whether it is displacement or we are looking at this thing. There's some other 4 vector. You will see something called the energy momentum 4 vector. That will also be there. Okay, so these kind of things we will do next lecture. Okay. And so right now I'm just formally, I wanted to show you E and B fields mix, and then we worked out what A and phi, how they mix, and we saw we had to modify Galilean boosts, and so we got some new object called Lorentz boosts. Okay, so we have to now work with Lorentz boosts, etc. And then now comes the thing: how does later after all this, we will see how should we modify mechanics. Okay, what I'm claiming is that mechanics has to be modified, not this thing, because the Lorentz force law, which is the origin of the U, for instance, one of the things has been tested pretty accurately to order U for sure. So, and it's weird that that's the only velocity dependent force that we have, and that so in some sense that has been tested and we know it well. Even before Maxwell unified things, we have tested, that was tested. It was done experimentally first. So, okay, so we will now move on to how, so what I'm trying to say is we need to modify Newtonian mechanics. Okay, and that is, after we'll have one lecture where we'll actually finish the Lorentz group and some definitions, and then we will go on to doing mechanics for 2 more lectures. Okay, is that clear?
Yes, sir.
So, the thing is, this was actually found by Lorentz well before, probably 5 years before Einstein, 1900, around that time. And Einstein wrote his paper around 1905, and he took all these things very, very seriously. So the way we have been thinking is more like inspired by Einstein, who just didn't work out the equations, but he asked what is the physics which underlies that thing, what are the implications. And he took the implications very, very seriously and pushed it to the extreme, and which we will see, well, it means a whole bunch of things. And so we will have to live with that. Okay. And it implies predictions to check in experiments, which we have checked. Okay. So at least terms order U square by C square and all, I think we have done experiments which have checked even those terms. Okay. So any other question?